Howdy folks, your friendly neighborhood root beer here, looking at question 3 on the 2015 Galois paper. So we've got 4 parts here, 1 light bulb where we just need sort of a very quick short answer, and then 3 written. So, A, if n plus 5 is an even integer, state whether n is even or odd. Okay, well, an odd number plus an odd number is always even. Which, while I'm at it, even plus an odd is always odd. And an even plus an even is always even. Now, what have we got? What situation have we got? N plus 5 is even and 5 is odd. So the only plus and odd that's equal to an even means it will have to have an odd. So all we need to do is state our answer. So odd. Odd would be what we would have filled in the box in the booklet. And here's my reasoning. I suppose I could write it out with an actual sentence or two, but I don't think it's quite necessary. It's probably only worth about 1 mark. Okay? Almost certainly 1 mark. I bet A is 1 mark, maybe B is 2 marks, C is 3, and D is 4, something like that. There's a lot of parts to this question, so we don't want to waste time writing for things that aren't even worth marks. B, if C and D are integers, explain why C times D times C plus D is always an even integer. So now, instead of addition, we're talking about products. How do you get a product to be an even integer? Well, product is only even if at least one factor is even. That's a nice true fact. You can say, well, okay, if 2 divides A times B, a product, 2 divides A or 2 divides B. This is a nice property that all prime numbers share. So if you wanted to be a bit more concrete, that's fine. But I say, this is a well-established fact here. You don't need the rest of this bit. So a product is only even if at least one factor is even. So if C or D are even, then we see CD, C plus D must be as well, since those are factors. And so if C is even, then you've got an even factor. If D is even, then you've got an even factor. The only case that isn't covered so far is what if both C and D are odd? So, however, if C and D are both odd, well, then we've got 2 odd factors here. What are we to do? That's what this third factor covers. So if C and D are both odd, then C plus D is even. And so we conclude CD times C plus D is still even. So that's enough reasoning. Maybe one mark for this case and 1 mark for this special case. I don't know exactly. I don't think I marked the Galois that year. If I was even marking it all that year. I think I marked in 2015. It doesn't matter. Does not matter. Alright, C. Determine the number of ordered pairs EF of positive integers where E is less than F, E and F is odd, so one of them is even, one of them is odd. That's the only way to have a sum that's odd. We sort of already remarked that. Okay, in fact, I can even write that down now. So the only way to make E plus F equal an odd is if exactly one of E or F is odd. 2 odds wouldn't do the trick. And so we'll need E is less than F. I don't know which one's going to be odd. We also have E times F is 300. Well, 300's even. So we actually don't need to worry about this exactly 1. E times F is 300, which is even. So at least one of E or F is also even. Okay. And we're not specifying which one is even or odd. So one of E and F needs to be even, the other one needs to be odd. So now let's look at pairs of factors of 300 where one is even and one is odd. Okay? I don't see why they need this EF condition. E less than F. I guess to make sure you don't double count the pairs, but E is never going to be equal to F, so you could have just had us count the pairs with the first number being bigger and the second one being smaller and not had to worry about that condition, but whatever. Alright, so I know 1 and 300, I mean that would have a sum of 301. 2, 3, 4 is a factor, so we'll get 150, 3, so 100, 4, 75. 5's a factor, that'll be 60. 6 is a factor, that'll be 50. 7's not. 8 isn't, because 2 is not a factor of 75. 9 isn't. 10 certainly is, so that'd be 10 and 30. Well, we'll continue on down here, I guess. 15 and 12. Oh, no, 12. 12 should do. Yeah, because 12 is a factor of 60. So 11 wouldn't work. 12 would work. 12 times 25. 13 won't work. 14 won't work. 15 will work. 15 and 20. Can't do 16 because we couldn't do 8. 17, obviously not. 18 is too much. 18 squared is 324. Alright, so let's look at these. That's an even and odd pair. That's an even and odd pair. So is this one. 2 and 150 are not. We need to make sure both factors of 2 are in the same thing. So only multiples of 4 will work here. So 10's actually out. 10 wouldn't work because 10 goes with 30 and they're both even. Same with 6 and 50. But the rest should all work. So 3 and 100, even and odd. 4 and 75, and 5 and 60. So that's 1, 2, 3, 4, 5, 6 such ordered pairs. I guess another way you could do this is say, you know, if you didn't want to write them all out, you could say, well, 300 is 4 times 75. In order to be even, you know, let's put all the 4's into one factor. And so it'll be 4 times A, comma B, where A and B are factors of 75. And just ask yourself how many pairs of factors of 75 there are. And there's going to be, well, that's going to be 3 times 5 squared, so that'll be 2 times 3. So that'll be 6 pairs of factors. No, not 6 pairs of factors. Those will be 6 different factors, and 4 goes with one of them. Doesn't matter which one. So that's another way to see it's 6. Anyways, it's 6 because it's 3 to the 1, so you do 1 plus 1 is 2. Then 5 to the 2, 2 plus 1 is 3. That's how you get 75. That's another quick way to do it. Doesn't matter. We wrote ours out, so we know that we're right. Alright, and now D part. Determine the number of ordered pairs mn, positive integers, so that m plus 1 times 2n plus m is 9,000. Okay. So we're sort of factoring, although they've stopped talking about this even and odd stuff. but maybe that'll find its way in somewhere. So 9,000 m plus 1, 2n plus m. Now if I add those up, maybe call this e and f. E plus f would be 2n, and then there's 2 m's plus 1, so it's odd. So once again, we've got e and f are odd, but they multiply to an even number. So, okay. It's almost the same sort of thing. 9,000 is going to be 8 times 9 times 125. E times f is even. E plus f is odd. Remember, E is, let's say, m plus 1. F is 2n plus m. Now, so anything else we can say? I mean, we do need to be mindful that m and n need to be positive integers. So, for example, E can't be the factor 1 and f 9,000 because then m would be 0. But I think just about anything else would be fine. I don't know, think about it. So, 1 of E or F, don't need that comma there, is even. There's not really any particular way to figure out which one is which. So, let us consider pairs of the form 8a and b, where AB is equal to 9 times 125, which I don't know off the top of my head. I'll just quickly grab the calculator. 1,125. There are 2 plus 1 times 3 plus 1. Again, the quick way to tell how many divisors a number has is to prime factor it, add 1 to each of the exponents, and multiply that all together. So that'd be 3 times 4, 12. Choices for A. Do all lead to M and N. Also, is 8A E or is 8A F? Things to consider. So, what could we have for A? A could be 1, 3, 5, 9, 15, 25, all the way up to 100, 1,125. I need 12 of them. Let's see, divide that by 3, you'll get 375. $225. 125. Surely 75 has got to be one of them. Yeah, that pairs up with 15. And then 25 and 45 go together. And that's 12 of them in total. Okay. So there's A. And then 8A would be 8, 24. B would be the other number. So 8, 24, 40, 72. We'll see how many of these I'm going to do. 120, 200, This will be 9,000. That's 1,000. I know that. 75 times 4 is 300, so that'll be 600. And I'm sort of tapped out. I'll just use my calculator. 360. I should have known that. 45 degrees. 225 times 8 is 1,800. 375 times 8, 3,000. The corresponding B's we can list. It's just the list in reverse order. So 45, 75, and 125. Alright, now, if m plus 1 is 8a, then m is equal to, and then n is equal to, so m and n would be, but what if m plus 1 is equal to b, then what is m and n? So m would have to be 100, just subtract 1 from b. 374, 224, 124, 74, 44. M would have to be 0 down here. 2, 4, 8. 15 goes to 14. 25 goes to 24. So we'd have M is 7, 23, 39, 71, 119, 199, 359, 599, 999, 1799, 2,999, 8,999. Alright, and now N. Is there a quick way to calculate N? Not really. You do F minus M and divide by 2. Alright, well, I'm just going to grab my calculator. So, 1,125 minus 7 divided by 2. This should always yield an N. But some of these B's can't subtract M's and have them be positive values. So, for example, 1 minus 8,999 still is even, but the M would be negative 4,449. Negative 4,499. There we go. So eventually there's going to be sort of a cutoff there. It's whenever M gets bigger than B, which makes me wish I'd done better bookkeeping. 75 minus 119 does not work. But 125 minus 71 is 54. Divide that by 2 is 27. And that one does work. I'll just fill in the rest of these ends. I won't do these ones. But we get 93 here. And 176 here. So this would be 1, 2, 3, 4 cases. And nothing else below, because the ends will be even. Similarly, whatever n is over here, we won't get a 0 there. Alright. So if m plus 1 is b, then that means my 8a is 2n plus m. So 9,000 we'll divide by 2, so that'd be 4,500 would be the n in this case. 3,000 minus 2 divide by 2 will be 1499. That one will work. And then again, there's going to be sort of this cutoff. 72 minus 124 is negative 52. And that'll be negative 26, so we won't be able to use that. But 120 minus 74 is 46. Divide that by 2. You'll get 23. So that'll work out. And these remaining ones should all do the trick. So 1, 2, 3, 4, 5, 6, 7. So it turns out there will be 11 possible pairs M and N. I'm just going to, because it's a video, I'm not crunched for time. I will complete this just so I have the full list. 200 minus 44 divided by 2, 78. 360 minus 24 divided by 2, 168. 600 minus 14 divided by 2, that'll be 293. 1000 subtract 8 divided by 2, 496. Oh, that's a perfect number. 1800 minus 4 divided by 2, 898. Just in case you're curious about all pairs, they didn't ask for the pairs. Determine the number of ordered pairs. Yeah, there we go. So 4 over here, and 1, 2, 3, 4, 5, 6, 7 down here. Can't have the last one here, can't have the last one here, and then there's one each. Only one allowed per row in those two columns, but I guess there we go. We have 11 possible pairs M, N. There weren't any other conditions like M less than N, just positive integers. And there we go. Okay, so not a whole lot to that one. I mean, it started off quite nice and neat with some odd and even work. D, I don't like it when we have to boil down to chart work, but it wasn't that bad because I did have my trusty calculator to speed things up. Looks like we got a little bit of geometry in question number 4, but I'm not going to spoil it for myself. I'm going to wait till the next video. I will, however, get myself a fresh sheet of paper in anticipation for the last question on the 2015 paper. Join me if you are so inclined. Thank you for watching.